Hi, today we're going to see about the working principle of DC motor. The statement of DC motor principle is very clear, very simple. It can be given in two lines. It is like this. Whenever a current carrying conductor is placed in the presence of the magnetic field, a force F is equals to BIL sin theta is exerted. I repeat, whenever a current carrying conductor is placed in the presence of the magnetic field, a force F is equals to BIL sin theta is exerted on the conductor, and thereby the conductor moves. This is how you can state the working principle of a DC motor. If you have to realize that with the help of the magnets, and with the help of these, the exact force, how is it being, how it can be exerted on the conductor, and what is the direction of the conductor in which it moves, and how Fleming's left hand rule will be able to predict the direction of the motor, all that stuff, if you have to understand, you need to go with me along. You need to come and you need to understand about this particular concept, what we're going to see for the next 10 or 15 minutes. See, what is that? The particular working principle, the statement, what is it telling is like, whenever a current carrying conductor is placed in the presence of magnetic field. So in that statement, how many elements are you finding? So current carrying conductor is to be taken, am I right? And then you need to take a magnetic field. So a conductor which has some current and then some magnets. Two elements are required. Okay, so let me take that two now here. So this is my magnet. Okay, hope it's not so clear. So I'll make it again. Okay, so let me indicate this as my north pole and this as my south pole. And what I do now, I take the rotor in the middle. So let me take the rotor slot here, one slot, and then the other side exactly I take another slot, and then I just put these two. I mean, this is my rotor, and this I call as conductor A, this I call as conductor A dash. Okay, something like the conductor is kept here and kept here. So what I have taken two conductors kept in the presence of magnetic field. Is it enough to have a motor? Check out with the working principle again. What is the working principle? Whenever a current carrying conductor is placed in the presence of magnetic field, not the conductor. So what I have to do, I'll take this particular conductors connected to a battery. So I connected a battery. This battery will feed some current into the conductor. Now the working principle is satisfied. Then what it says, what it says, then this conductor is exerted by some force which is F is equals to BIL sin theta. This is very good. Understanding until this point is very easy, right? So statement understanding and realization is very easy. But how is it exactly going to exert? How is that force exactly going to be exerted? On the conductor? Okay, let us understand that, right? I take the battery connection, okay, so I take a supply voltage VDC which feeds a current called IDC, okay, and not only that, I just indicate the flux lines which are moving from north pole to south pole, okay, north pole to south pole. These are the flux lines which are moving. This is your flux, let's say main flux, right, moving from north pole to south pole inside the motor. This is actually a simple motor where I have taken two poles and two conductors. Two coil sides are considered to be one coil. Okay, so what I have to take up next? Let's see that there is, so whenever you give some current to the conductor A and A dash, okay, then A and A dash also will have their own flux. I mean to say, this conductor will have its own flux, and this conductor will have its own flux. To be practical, when you give current like this, and this current goes inside the conductor A and then comes out of conductor A dash. Is that clear? So what is the current direction in the conductors now? One is going in, the other is coming out. Am I right? Okay. So now see what will happen. What is a flux? I mean, as I said, this conductor, as there is some current flowing through this conductor, there will be some flux of its own. And this conductor, as the current is coming out, there will be some flux of its own. Okay. Now, what is the flux that is produced by conductor A? Conductor A. So according to the Ampere's thumb rule, whenever you take a conductor and give current in the direction of thumb, then what happens, my dear? What happens? So whenever you give current in the direction of thumb, then the flux is produced in the direction of curled fingers. Something like this, curled fingers. Suppose if you provide current in this direction, in the direction of thumb, then this will be giving a flux in the direction of fingers. Very simple. If the current direction is in the direction of thumb, then the flux will be in the direction of fingers. If you can see this, if the current is coming outwards, see my hand clearly, if the current is coming outwards, then the flux direction is, what is it? Anti-clockwise direction. If the current direction is going in, then the flux direction will be for you it will be clockwise direction. Now let us try to understand. If the current direction is going in, let's see, going in, then what will be the flux direction here? The flux will be directed in the clockwise direction. And what about this conductor A dash? Here also conductor A dash will have its own flux, and the direction of flux is determined based on the Ampere's thumb rule. As the conductor current is coming out, then the flux will be in the direction of the fingers, the coming out, and this is the flux direction in the fingers. And this is my flux phi A dash. This is a flux phi A. Very nice. Until this, it's very good. Now, the thing what I'm going to explain will make it very clear for you to understand the working principle and to even know about the direction of the motor, in which direction it rotates. See now, how many flux components are there? Basically, one is a main flux called field flux. The other is the armature flux. What is that? How many components? One is a main flux or field flux, the other is the armature flux. In fact, main flux is only one component. Armature flux is about two components in two different conductors. Let's say if you have a armature of 100 conductors, usually in a real-time generator you will have hundreds of conductors. So all the conductors will have its own, their own current. I mean their own current direction, and thereby their own, flux. So if the current direction is inwards, you'll have the flux in the clockwise direction. If it is outwards, it will be in the anti-clockwise direction. Hope you are going with me. So how many components of flux are present in the armature in my motor? A simple motor with a simple single loop armature conductors. Armature coil with two conductors. So I have two flux components. Now what will happen whenever you have two flux components? They definitely do interact. What happens? These flux components do have some interaction. So how do they interact? See here now. The flux phi m is moving from north to south, right? So if you clearly see on the top of this conductor, this flux phi a, am I right? Phi a and phi m both are in the same direction. Can you observe that? See my hand? It is like this, right? And this flux is also going in the same direction, which means on the top of conductor A, above conductor A, you will find phi m and phi a. Both are in the same direction. Okay, both are in the same direction. Then what happens, teacher? I'll explain that later. So next one is to the bottom of conductor A, to the lower side of conductor A. What is happening? Can you check out the direction of phi A below the conductor A? See here, it is going this way, which means the flux phi m is coming in the same direction, but phi A is clockwise, right? So it goes under this conductor A and moves inside this north, it moves like in the clockwise direction, where you can find below conductor A this phi A and this is phi M are not in the same direction. Get my point? In this lower portion of under the conductor A, you will have phi A and phi M in the opposite direction. Let me indicate that here. So phi M is in the same direction and phi A is in the opposite direction. Okay, is in the opposite direction. Okay, right? Then what will happen? So what will happen is all the flux lines, the flux lines which are traveling here will come here, or will go this way. The flux lines which are moving this way will be opposed by this flux. Am I right? Will be opposed by this flux. Usually they have to move towards the south pole, but this flux which is there on the top, the phi A flux, when it is coming down, it opposes the main flux here. So the flux lines will tend to get opposed, will get opposed by the phi M is opposed by phi A, which means this to the lower side of conductor A, you will find the flux, the net flux will get weakened. You know why? Because phi A is opposing phi M. So the flux which is traveling here will be opposed by armature flux. Then what will happen? This flux will not try to go this way. It will bend and try and go and join in align with phi A, because phi A is in this direction here. So it moves on and then goes into the armature. This is how it moves. Why like this? Because to the lower side of the conductor A, there is a opposition. The flux lines would get cancelled. So the flux lines will experience a opposition here. So it tries to bend over and then go along with, go above conductor A. Hope you are getting me, right? So why? Because here the flux direction is like this, right? So phi A is in line with phi M. So here there is no opposition, so it moves like this. Then it is the flux, all the flux lines, majority, 98% of the flux lines will go this way and only 2% will come this way and may reach. So together, altogether I can say very less amount of flux will travel this way because of the opposition, and maximum amount of flux will go over the conductor A. Okay, now you see the flux lines are coming this way, right? Okay, what about here? Here, if you can see clearly, this flux, A dash flux, is in the anti-clockwise direction. Am I right? So on the top of the conductor A dash, here on the top, phi M is as it is from north to south, phi M the main flux, but phi A is, what is happening? Phi A is opposing the main flux. Am I right? Is opposing the main flux, phi A dash. Are you understanding? So on the top, above conductor A, there is a big opposition for the flux because phi A dash is opposing the mainstream flow of flux. So here, because of this opposition by phi A, very less amount of flux will go this way. Majority will get deviated and then move where? Under the conductor A dash, under the conductor A dash. You know why? Because here the flux direction is in the same direction as phi M. So what is the flux direction here? At the bottom of the conductor A dash, the flux direction is phi M, and if you are taking the current flux direction of phi A dash, it will be in the same direction as phi M. So here there is no opposition, here there is no reluctance. This flux will not oppose the mainstream flow of flux, rather it gets aided. It gets aided, but here the flux will cancel, will get will be opposing the mainstream flow of flux. So here, but this one under the conductor A dash, you will find phi A dash is not opposing, is getting added or aided with main flux phi M. So all the flux lines, instead of going this way, because there is an opposition, it tends to move to the lower side of conductor A dash. This is how it moves to the north to south. What is happening, my dear? What is happening? Are you understanding what I'm trying to say here? When you switch on here the current through the armature, okay, then all this happens. If you don't switch on, then the flux from north to south will move as it is, like a straight line. But when you are turning on the current that is flowing into the armature flux will come into picture, and this armature flux will oppose the main flux. Conductor A, on the top of the conductor there is no opposition, it is getting aided, so all the flux will move like this. But to the bottom there is an opposition, so it doesn't move there. Okay, so the flux will not tend to move in this direction, under the conductor A, rather it moves above. Okay, and then coming to this side, the flux lines will tend to move under conductor A dash. You know why? Because there is a flux direction of phi A dash is in the direction of phi M. This is how you will find the magnetic flux lines, which are supposed to be like a straight line, which are intended always to be like a straight line, will get bent. What is happening to the flux lines? Flux lines are getting bent. So flux lines are like elastic, elastic wires. It has got the property of elasticity. It doesn't bend. Even if it bends, it doesn't. The flux line could not sustain in the bent position for a long. It tries to come back. So how it tries to come back? Let me tell you now how it tries to come back. See. So the flux lines are like this, right? See my hands? The flux lines are like this moving, right? So because of the elasticity property of these flux lines, the flux lines will try to become like a straight line. It tries to become like a straight line. In that process of flux lines trying to get back to its original shape or original state, you can say, in order to get back to the original state, these flux lines which are concentrated, which are moving on the top of conductor A dash, will push this down. Which one will push this conductor A down? And the the flux lines which are under the conductor A dash will push this conductor A dash up. Something like this. See my hands? So it is like this, right? So in the process of coming back to the normal state, this conductor A is pushed by the flux lines down, okay, and this flux lines will push conductor A dash up. It's something like this. The flux lines, and then they push. When this is pushed, then what will happen, my dear? When this is pushed, this conductor A dash will move in the anti-clockwise direction, and conductor A will move down. It moves up and it moves down. So finally you get a rotation like this. And when you connect a shaft here, the shaft rotates in the anti-clockwise direction. Do you understand how the flux direction is affecting, flux interaction is affecting the whole rotation of the motor? If you wanted to run your motor in the clockwise direction, you can do it by changing the direction of the magnets, or by changing the direction through the conductors. Either of these you have to change. If you change both, again the direction of the motor will remain same. Are you understanding, my dear? So hope you get a good point in this lecture. So what is that? The flux direction, the interaction of flux is very important, is very crucial to understand if you have to understand the working principle of the motor. So the rotation of motor, the outcome of motor, is decided based on the flux interaction. And to be specific, this particular experimentation, what Fleming's, when he was doing, he understood the motor direction, and then he gave us a law called Fleming's left hand rule. I will explain that also in this lecture itself. So what is that Fleming's left hand rule? There is all three fingers are to be kept perpendicular to each other. So my index finger is indicating about the flow, flux direction, and the middle finger is indicating about the current direction through the conductor, and this is indicating about the motion of the conductor or the movement of the conductor. Okay, now you will see how Fleming's has got this idea of implementing this. He did not do anything miraculous there. He just observed this and then put his fingers and got this law by himself. See how he has done it. So he took the current, flux direction in the direction of index finger, north to south, yes, and he took the current direction that is flowing into the armature conductor in the direction of finger. Okay, so what is that? These two, these are the predictors, to say these are the input. I would know, because I know the flux and its direction in the motor, and I know the current direction through the conductor because I am giving the supply. So here if you see in this conductor how the current is coming out, right? The current is coming out. So the current is coming out and the flux is from north to south. Get my point? The current is coming out, which I am giving, and the flux is moving from north to south in the direction of the index. So index finger and then current, middle finger, flux direction, current direction. Then what? The movement, it will be in the direction of, now stretch forth your third finger, thumb finger, it will give the direction of the conductor. So what is it? It is the conductor A dash should move up. That is what is happening here. That is what is happening here. This is how Fleming's has understood that yeah, this can be put in these three fingers and we can propose, and he proposed and it is a great patent in his name. We can tell anywhere in the world without seeing the motor, just by saying this, like this is how it is. Flux direction and current direction predicts the direction of the motor. And if you want to understand here the current direction is flux direction is in the same direction from north to south, and the current direction will be inwards, right, into the board. Okay, let's take this finger into the board. Okay, then the flux direction is my index finger, and the middle finger is indicating what? The current direction, which is into the board, inwards, and the movement of the conductor will be downwards. This is how you can understand about the movement of the conductors, and thereby you can say that whether it is clockwise direction or anti-clockwise direction. This is how you can understand about the Fleming's left hand rule. So this is what is the entire working principle and its description. And coming to the force, what is this force? As stated in the working principle, as stated in the working principle, F is a force that is exerted on two conductors, thereby the force that is exerted, on two conductors, thereby this phi A dash could go up and A conductor could come down, and thereby the rotation can take place. And the force which is exerted for the rotation is equals to BIL sine theta, where theta indicates the angle of rotation of the conductors or the armature itself, and this is the length of the conductors what you have used for the in the armature and in the windings, and then I, the current, that is the magnitude of the current that is flowing into the armature conductor, and thereby and the last one is B is magnetic flux density, that is depicted or described by the magnetic field intensity, by the flux per unit area. Okay, the flux that is being spread by these two field poles. This is how you can understand about the working principle. See you in the next video lecture. Thank you.